Okay, let's unpack this. We often talk about physics in terms of stability. We build entire mental models around systems that are in equilibrium, the perfectly stable, balanced end state.
Right, the finish line.
But let's be honest, true equilibrium is, well, it's a bit boring. The real action in the universe happens when systems are trying, often desperately, to get to that balance.
That's absolutely right. Equilibrium is the thermodynamic goal. But today, we're stepping off the sidelines and onto the field to study the game itself. We are diving into non-equilibrium thermodynamics.
Specifically, we're focusing on the dynamic processes known as transport phenomena. Our mission is to tackle a question that, the most famous law in physics raises but never actually answers. The second law of thermodynamics is brilliant. It gives us a compass.
It tells us which way to go.
Exactly. It tells us which way a spontaneous process goes, always towards increased entropy, towards maximum disorder. But it's totally silent on the clock. It doesn't tell us how fast that happens.
And that speed, that rate of flow, whether it's the flow of energy or mass or even momentum, is what defines our reality. The entire study of transport is about quantifying that speed.
So let's start with that fundamental drive, the engine of flow itself. We need to confirm the direction. So imagine the simplest possible scenario. You connect a hot thermal bath, let's call it T$1, to a cold thermal bath, T$2.
Okay.
We all know the heat flows spontaneously from T$ to T$2. But why is this direction? Why is it mathematically mandated?
It all comes down to where the entropy change is measured. When heat, let's call it a quantity, transfers, it creates two opposing changes.
Okay.
The cold bath, T$2, gains that heat, so it gains entropy. We'd write that as a positive change, delta S22, which is simply $2 divided by its temperature, T$2.
And the key there is that the denominator, T$2, is a small number because it's cold.
Exactly. Now, at the same time, the hot bath, T$1, loses the same amount of heat, $T, so it experiences a negative change in entropy, delta S01, which is $2 divided by its temperature, T$1.
And since T$1 is hotter, the denominator there is a larger number.
Precisely. So the magnitude of the entropy loss in the hot system is less significant than the magnitude of the entropy gain in the cold system.
So the universe's net profit is positive.
Always, because T$1 is always greater than T$ in this scenario. The positive gain, delta STOS, always outweighs the negative loss, delta S on 1. So the total entropy change for the entire universe, the two baths combined, has to grow.
And that confirms the process is spontaneous. It's irreversible.
It forever pushes the system towards that maximum uniformity and disorder.
There's even a beautiful, elegant formula in the source material confirming this. It involves the final mixed temperature, T⁻.
Right, the total entropy change, delta S, is proportional to the logarithm of a fraction.
The fraction is T⁻² on top, divided by the product of the initial temperatures, T⁻1 times T⁻shizzles on the bottom.
And what's so fascinating here is how that formula proves the direction if you understand a little bit about mathematical means. The final temperature is basically the arithmetic mean of the two temperatures, the average.
Okay.
But the denominator, T gallon times T$2, is related to the geometric mean.
Ah, I think I see where you're going. The arithmetic mean is always greater than the geometric mean, unless the two numbers are identical.
Correct. The moment T$1 and T$2 are different, the numerator in that fraction will be larger than the denominator. This makes the whole ratio inside the logarithm greater than 1.
And the logarithm of any number greater than 1 is positive.
Which means the total entropy change, delta C, must be positive. It's this elegant mathematical guarantee that flow must occur until T$1 equals $2.
So we have our mandate for the direction,
Yeah.
hot to cold. But as we said, the second law only provides the compass. To find the rate of that heat flow, the speed, we need to talk mechanics. We need to talk about conduction.
Right. To measure speed, we have to start defining our terms rigorously. We begin with heat flow, which we often just call power, or per solar.
That's the amount of heat energy,
Yeah.
dan Q dollars, transferred over a certain amount of time, dt dollar.
Yes, joules per second. We measure it in watts.
But a watt is a measure of total transfer. If I have a tiny metal spoon and a massive metal slab, and they're both transferring 100 watts, that spoon is doing a much better job relative to its size, right? We have to account for the physical dimensions.
We absolutely do, and that's why we introduced the concept of heat flux density, which we denote with a lowercase Downey dollar.
So this is the flow per unit area.
Exactly. It's the power divided by the area. Think of it as intensity. We're now measuring the energy flowing per second through a single square meter of material.
And this quantity, this heat flux density, dAtal, is what connects our macroscopic observation to the microscopic driving force.
And that driving force is simply the spatial change in temperature. The steeper the hill, the faster the energy rolls down it.
Which brings us to the foundational law for this kind of transfer.
Fourier's law of heat conduction. It dictates that the heat flux density, J.H. is proportional to minus lambda, that's the Greek letter, lambda, times the spatial gradient of the temperature, $2.
Okay, let's break down that gradient for a second. The gradient of the dollars is just a mathematical way of measuring the slope, right? The rate of change of temperature over distance.
If you move 1 meter in a certain direction, how much hotter or colder does it get? That's the gradient.
So the steeper that slope, the higher the gradient, and the faster the resulting flow, J-sha.
Correct. And now we have to talk about that crucial minus sign we included, J-A-J-R West-A-Taller text gradient, T. That little minus sign is the second law, embedded directly into the physics of flow.
How so?
Well, the temperature gradient, by mathematical convention, always points in the direction of increasing temperature, but heat must flow in the opposite direction, from high T to low T.
So the negative sign ensures that the heat flux is flowing against the mathematical gradient. It flips the direction.
It enforces physical reality. And that other term, lambda, is the material constant. It tells us how good a specific material is at this process.
That's the thermal conductivity.
That's it. It quantifies the intrinsic ability of a substance to pass thermal energy through itself. And you see just astronomical differences in lambda values between materials.
We talked about metals being thermal powerhouses.
Take silver or copper. They have lambda values around 400. This incredible efficiency comes from their atomic structure. They have a sea of free electrons.
So these electrons aren't tied to any single atom.
Exactly. They just roam through the whole lattice, carrying energy and momentum extremely rapidly. This is why metals are simultaneously excellent electrical conductors and thermal conductors. The mechanism is the same: high-speed electron transport.
And then on the other end of the spectrum, you have the poor conductors, the insulators, materials that rely on just atomic jiggling.
That's a great way to put it. The energy transfer in insulators like glass, which has a lambda of about 1, or water with a lambda of about 0.5, relies on tiny vibrations passing from one fixed atom to the next. These are called phonons.
So it's like a very slow, inefficient game of telephone.
A very slow game. The energy transfer slows dramatically.
And then the superstar of insulators, air, its lambda is only 0.024. But you give us a crucial warning about that.
Yes. Air is an excellent insulator, but only if it is completely stagnant.
You have to stop it from moving.
You have to. If you can stop it from moving, its low density means its molecules are so far apart that energy transfer by direct collision is incredibly rare. If you allow air to move, however, it becomes a superb conductor through convection, which we'll get to in a moment.
Okay, so Fourier's law gives us this instantaneous snapshot of flow. But the dynamic process, the actual heating up or cooling down of something over time, requires us to look at conservation.
Right, we have to move from the instantaneous rate to the temporal evolution. We do this by performing a balance on an infinitesimally small volume element. We have to account for the rate of heat flowing in versus the rate of heat flowing out.
And if the inflow rate is greater than the outflow rate, that excess heat energy gets trapped in the volume.
And that trapped energy must manifest as a temperature rise.
Okay.
Mathematically, this net flow into the volume is related to the negative divergence of the heat flux density. If you have a net convergence, you have an accumulation of heat. We then link this accumulation rate to the temperature rise using material properties.
The heat trapped, dq Bellers, must equal the density, times the volume, times the specific heat capacity, times the change in temperature, dV.
And when you combine that energy conservation balance with Fourier's law, when you substitute the relationship between flow and the temperature gradient, you get the masterpiece known as the heat conduction equation.
And its final beautiful form shows that the rate of temperature change over time, dt dt, is proportional to the Laplace operator applied to the temperature field, delta tt.
So ddtt propto delta t.
And the proportionality factor, the quantity that really governs the speed of this entire process, is lambda.
That proportionality factor has its own name. It's called the thermal diffusivity. It is the absolute key to predicting how fast thermal changes will spread through a material.
Let's unpack that factor for a second, because that fraction is loaded with physical meaning. Why does low density speed up this process, and why does high specific heat slow it down?
Think about the two sides of that fraction. Lambda, the thermal conductivity, is in the numerator.
Right.
A high lambda means heat travels easily through the material. It's a faster engine. So high conductivity means faster propagation of temperature changes. That makes sense.
Okay, that's intuitive.
Now look at the denominator, which has density, chlors and plurs, and specific heat capacity, sort dollar. High density means more mass packed into a given volume. High specific heat capacity means that mass requires more energy to raise its temperature by 1 degree.
So both ring and rider act as a kind of thermal inertia.
That's the perfect word for it. Materials with high inertia, heavy materials that soak up a lot of energy, are slower to change temperature, even if their conductivity is high.
So you could have something that conducts heat fast, but heats up slowly overall because it's so massive.
Exactly. Understanding that balance is crucial for engineering. But the truly unifying conceptual idea here is wrapped up in that Laplace operator, a delta Taylor. You called it the dentedness of the temperature field. What does the universe do with that dentedness?
Right. What is the physical meaning of the Laplace operator here?
The Laplace operator, delta Taylor, is a measure of curvature. It tells you if the temperature at a specific point is higher or lower than the average temperature of its immediate neighbors.
So if delta T is positive, you're in a cold valley surrounded by hotter neighbors.
And if delta T is a negative, you're on a hot peak surrounded by colder neighbors.
And what the heat conduction equation states is that the rate of change in temperature, delta T test, is directly proportional to that very dentedness.
Yes. If the temperature curve is dented, if that second derivative is non-zero, the laws of physics immediately mandate action. The heat conduction equation is the great smoothing machine of physics, the Gluttung's machine.
A smoothing machine, I love it.
If you have a hot peak, delta T will be negative and the peak cools down. If you have a cold valley, delta T will be positive and the valley warms up. The system acts to relentlessly flatten the temperature landscape until delta T is zero everywhere.
It's a beautifully simple universal command. The entire process of conduction is just the universe working to achieve thermal uniformity one tiny step at a time.
It's the slow, local pursuit of thermal equilibrium, a localized heat death.
Okay, so conduction is how energy moves through static matter. But when we talk about fluids, gases, or liquids, a much more dramatic and, frankly, faster mechanism kicks in: convection.
Convection fundamentally shifts how energy gets carried. In conduction, we were relying on particles handing energy off to each other while staying in place.
The handshake model.
With convection, we abandon the handshake. We transport the energy carriers themselves. We move the mass, and the mass carries its heat along with it.
And this reliance on mass movement means we need gravity and we need density differences. The classic example is heating a pot of water on the stove.
Exactly. When you heat that fluid from the bottom, the layer closest to the heat source expands. Crucially, its density drops because the same mass now occupies a larger volume.
And that lower density fluid is buoyant. It wants to rise.
It's driven upwards. And at the same time, the colder, denser fluid from the top sinks down to take its place near the heat source. This establishes a continuous circulatory loop.
The roller vortex.
The roller vortex. And this mechanism is incredibly efficient at transferring vast amounts of energy very quickly.
And sometimes when these fluids are driven hard, far from equilibrium, they don't just swirl randomly. They self-organize into these spectacular, highly ordered structures. Which brings us to the mesmerizing world of Rayleigh-Benard cells.
This is truly where physics becomes art.
It is. What is the precise mechanism that causes these ordered structures to form?
Imagine a shallow layer of fluid being heated perfectly uniformly from below. At first, heat is just transferred by conduction, the slow way. But as the temperature difference between the top and bottom layers increases, that density difference grows.
So at some point, the buoyant force overcomes the internal friction of the fluid, the viscosity that's trying to hold it still.
That tipping point is quantified by a dimensionless number called the Rayleigh number. When the Rayleigh number exceeds a critical value, it's around 1,708 for an idealized system, the system just snaps. It transitions from random thermal noise into spontaneous ordered flow.
And it organizes itself into these regular geometric cells, often hexagons.
Yes, typically hexagons, to maximize the efficiency of heat transfer. The system, when stressed, finds the most optimized geometric pattern to achieve its thermodynamic goal, which is evening out that temperature gradient.
So in these hexagonal patterns, the hottest fluid rises right up the center of the hexagon.
And the cooler fluid sinks along the hexagonal walls. It creates this beautiful honeycomb-like network of perfectly spaced convection rolls. It's a phenomenal demonstration that instability doesn't just lead to chaos. It can lead to complex functional order.
And the scale of this phenomenon is breathtaking. This isn't just a petri dish experiment.
Oh, not at all. We see these patterns writ large all over nature. On the surface of the sun, what astronomers call solar granulation. Those are essentially giant Rayleigh-Bernard cells.
Kidding.
Not at all. Enormous masses of plasma are transferring heat from the sun's interior to the surface in these cells. Each granule can be hundreds of kilometers across.
So when we look at a high-resolution image of the sun's surface, we are literally watching the universe execute this process, but with an added layer of organized mass transport.
Exactly. We also see it on Earth in atmospheric dynamics, certain cloud formations, patterns of fog. Sometimes you can see these large-scale cellular structures as heat rises from the ground, organizing the air masses into these same convective rolls.
It's incredible.
Yeah.
So if conduction and convection are the primary ways heat moves, what if our goal is to stop the movement? This is the science of insulation.
Right. And our strategy for insulation is built entirely around defeating those two mechanisms, especially convection. The goal is to maximize what we call thermal resistance, or $2.
We already established that stagnant air is the best everyday insulator we have, with that incredibly low lambda value of 0.024.
So if air is the insulator, the entire trick of modern insulating materials, dumb stuff like fiberglass or down or styrofoam, is not that the solid material itself is some magical insulator.
It's that the solid material is engineered to trap air.
To trap air and hold it perfectly still? They break up the space into millions of tiny microchambers so that the air pockets are too small to form those efficient convective roller vortices.
You're blocking the convection.
You're blocking the convection. And once that's blocked, the only path for heat loss is through the slow, poor mechanism of conduction, either through the stagnant air or the thin, low conductivity structure of the foam or fiber itself.
And bringing this to a practical application, like in construction, we use that thermal resistance, $3, to calculate the overall efficiency of a wall.
And $3 is simply the thickness of the material divided by its conductivity, lambda.
Okay.
And here's a beautiful practical application of this physics. When you calculate the efficiency of a house wall, the thermal resistances of all the different layers, the drywall, the insulation, the brick, they simply add up in series.
Just like adding resistors in a basic electrical circuit.
Exactly the same principle. Vortex total R1 plus R2 plus R3, and so on. This means if you have one really great layer of insulation with a high raw value, that resistance will dominate the total, making the other layers almost irrelevant to the overall heat loss.
Which is why insulation is so critical.
Precisely. And in construction, that overall heat transfer coefficient you hear about, the K value or the U value, is simply the reciprocal of that total thermal resistance. Higher resistance, lower U value, more efficient wall. Transport physics directly dictates your heating bill.
We've covered energy transport. Now we turn our focus to the equally relentless transport of mass.
Yeah.
Just as the universe tries to smooth out temperature differences, it tries to smooth out concentration differences. And it does that via diffusion.
Diffusion is the material counterpart to heat conduction. It's the spontaneous movement of a substance driven entirely by the existence of a concentration gradient, molecules moving from regions of high concentration to regions of low concentration.
The drop of ink spreading in a glass of water. The smell of perfume crossing a room. No external stirring needed. Why is this spontaneous? What's the driver?
The driver here is pure, overwhelming statistics, and it's rooted in entropy. Every single particle in the system, whether it's a water molecule or an ink particle, is constantly undergoing Brownian motion.
That random, energetic, microscopic jiggling due to thermal energy.
Right. So if all the ink is concentrated in one spot, the particles are constantly bumping into each other, trapped in a small space. Statistically, a particle's next random step is overwhelmingly more likely to take it toward a region where there are fewer particles.
Is because there's more empty space to move into.
There's more available space there, exactly. Yeah. The system favors the maximum number of possible configurations, and the state of maximum entropy is the state where the particles are perfectly spread out, making the concentration uniform everywhere.
So the concentration gradient we see is just a visible manifestation of an underlying probability gradient.
That's a perfect way to put it. It's the drive to maximize configurational entropy. And to quantify this flow, we turn to Fick's laws, which, almost unbelievably, have the exact same mathematical structure as Fourier's laws for heat.
So first, Fick's law describes the instantaneous flow.
Yes. The first Fick's law states that the particle flux density, $, that's the number of particles moving per second through a unit area, is proportional to minus the diffusion coefficient, $ times the concentration gradient of the substance, $.
The X gradient and $. It's identical in form. The particle current flows opposite to the concentration gradient, toward lower concentration.
And $1, the diffusion coefficient, is the measure of particle mobility. Just like lambda for heat, dollars defines the material's personality. It's a huge value in gases, where molecules can travel a long way before colliding.
And much smaller in liquids.
Significantly smaller in liquids, where particles face constant viscous drag, and it's vanishingly small in solids, where atoms are mostly locked in place.
Okay, so to understand how the concentration profile changes over time, we move to the temporal law, second Fick's law.
And this is derived using the conservation of mass. Just as we did with heat, we look at a small volume element and we balance the mass flow in versus the mass flow out. The net accumulation rate has to relate to the change in concentration over time.
And when you combine that mass conservation with the instantaneous flow from the first Fick's law,
You arrive at the second Fick's law. Dep in dollars is equal to double dollars times the Laplace operator applied to the concentration field, delta N dull.
delta N dollar. This is the moment where the real power of non-equilibrium thermodynamics becomes so apparent. The mathematical engine governing mass flow is the same as the engine governing heat flow.
It is the ultimate confirmation of this unifying principle. Diffusion is the mass smoothing machine. It sees a dent in the concentration field, a high peak or a low valley, and it acts relentlessly to flatten it out. The universe doesn't care if it's smoothing temperature or smoothing concentration. The mechanism, dictated by probability and conservation, is identical.
Which means whether I am waiting for heat to travel across a piece of metal or waiting for sugar to dissolve completely in my coffee without stirring, the propagation speed is determined by the exact same mathematical framework.
It's the universality of the smoothing process. Everything tends towards flatness and uniformity because that is the state of maximum disorder, maximum entropy.
This concept of diffusion, this mathematical drive to smooth things out, became the ultimate tool for solving one of the greatest scientific debates of the early 20th century, proving definitively the physical existence of atoms.
And we can do that by examining this tiny, elegant battle between gravity and diffusion.
What's the setup?
The setup, first explored rigorously by Jean Perrin and then fully explained by Einstein, is simple. You take a suspension of very small but still microscopically visible particles like pollen grains or tiny latex spheres and suspend them in a liquid like water.
Okay.
These particles are now subject to two powerful opposing forces.
The first and most obvious one is the external force, gravity.
Gravity pulls these particles downward. This is called sedimentation. But because of the viscous drag from the liquid, they don't accelerate forever. They quickly reach a constant terminal sinking velocity of Euler's.
And that viscous drag, that friction force, is defined by Stokes' law.
Right, it's proportional to $6 PE or Vy, where ALA is the liquid's viscosity and $3 is the particle's radius. This downward movement creates a steady sink current, which causes the particles to accumulate at the bottom of the container.
And the moment particles accumulate at the bottom, the concentration, $, becomes extremely high there and low at the top. And that immediately introduces our second force.
The spontaneous upward current driven by diffusion.
So the concentration gradient created by gravity then drives an opposing upward movement trying to restore uniformity.
And that upward flow, ds, is defined by Fick's law. It's driven by the random buffeting of the particles by the surrounding water molecules, that's Brownian motion, which pushes them back up the gradient.
So we have a stable system, an equilibrium, when the gravitational sink current pulling down is perfectly balanced by the diffusion current pushing up.
Exactly. And when you set the formulas for Stokes friction and Fick's diffusion equal to each other, you get a differential equation. And when you solve it, you get a curve describing the concentration of particles, non-dol, as a function of height, $1.
And the resulting mathematical function is immediately recognizable to anyone who studied physics.
It is an exponential decay function. The concentration is proportional to $5 raised to the power of some negative constant times height.
That is precisely the mathematical shape of our atmosphere, the barometric height formula, which shows air pressure decreasing exponentially with altitude.
And here is the genius move. This is the bridge from the macroscopic world of transport to the microscopic world of atoms. We look at that exponent. From the fundamental principles of Boltzmann statistics, we know that any equilibrium distribution in a conservative force field like gravity must contain the ratio of potential energy to thermal energy.
Okay, so the potential energy here is the particle's gravitational potential energy.
And the thermal energy is kBg, where kBeller is the Boltzmann constant, the fundamental link between temperature and the kinetic energy of individual particles. So Boltzmann statistics mandates that the exponent must be no to h kBa.
So we have two different formulas for the exact same physical profile. One derived from flow and friction, from transport physics, and one derived from pure statistics and energy from thermodynamics. They have to be identical.
They must be. So we simply compare the coefficients in the exponent. And by equating the coefficient we derived from Fick and Stokes to the coefficient mandated by Boltzmann, we can cancel out the variables and derive the stunning Stokes-Einstein relationship.
Which is a...
d equals kBT, 6 pi at AR.
That equation is beautiful. It links the observable movement of a particle, its diffusion coefficient, dollar and the temperature, the resistance of the medium, and the particle size. But most importantly, it isolates that tiny microscopic constant kb.
Which brings us to 1905, Albert Einstein's miracle year. At the time, while many scientists accepted atomic theory, there were still fierce debates. Skeptics argued that atoms were just a mathematical convenience.
There was no direct physical proof that could actually quantify the size of a molecule.
Einstein realized that the Stokes-Einstein equation was that proof. He proposed that if you meticulously observed the random, erratic dancing of suspended particles under a microscope, the classic Brownian motion, you could measure their diffusion coefficient, dollars.
And you could also easily measure the liquid's viscosity and the temperature.
$2. So you take those measurable microscopic parameters, the jiggling speed, the liquid's thickness, the temperature, you plug them into his equation, and you can calculate dollars, the Boltzmann constant.
And because kilobar is directly related to the ideal gas constant and Avogadro's number, calculating kilobars allowed Einstein to calculate Avogadro's number for the first time with real precision.
Yes. And that number is the bridge between the mass we measure in the lab and the actual number of individual atoms. This was the first truly rigorous, quantitative, and indisputable physical evidence that atoms and molecules actually exist, and it gave us their size.
All from watching dust dance in water. It's an incredible testament to how understanding simple transport phenomena could fundamentally shift our view of the universe.
It really is.
And that drive for concentration equalization via diffusion takes us into the world of biology, leading to another spectacular phenomenon: osmosis.
Osmosis is a specialized form of diffusion across a selective barrier, a semi-permeable membrane. This barrier is picky. It lets the solvent, usually water, pass through freely, but it completely rejects larger solute molecules like sugar or salt.
So let's set up the classic scenario. A container separated by this membrane, with pure water on one side and concentrated sugar water on the other.
The concentrations are clearly not equal, so the universe mandates smoothing. The water, seeking to dilute the sugar and equalize the concentration, begins to diffuse across the membrane, moving from the pure water side to the sugar water side.
And since the sugar molecules are physically blocked, the water just keeps flowing in.
That influx of water causes the level of the sugar water solution to actually rise, building up a hydrostatic pressure differential, and that pressure pushing back is the osmotic pressure or pression.
So the flow continues until that accumulated hydrostatic pressure is strong enough to mechanically stop any more water from coming in.
Exactly. At that point, the system is in equilibrium, not because the concentrations are equal, but because the pressure difference perfectly counteracts the entropic drive of diffusion.
The mathematical law governing this osmotic pressure, discovered by Jacobus Henricus van Hoff, is, in my opinion, one of the most astonishing connections in all of physical chemistry.
It truly is. Van Hoff found that the osmotic pressure multiplied by the volume of the solution, O balls, is equal to the number of moles of the solute, nu times the ideal gas constant, $3 times the temperature, T.
Wait a minute. Say that again? C.RELREUSD?
Yes.
That is mathematically identical to phi.RELC. It's the ideal gas law.
It is the ideal gas law.
We're talking about sugar molecules dissolved in a liquid, a state completely removed from a gas, yet they're exerting pressure exactly as if they were a gas. They are the ideal gas imposter.
That's it. The dissolved solute molecules behave thermodynamically as if they are free gas molecules occupying that volume fighting to expand and fill the container. They exert a pressure on the membrane that is analogous to the pressure a gas exerts on its container walls.
It reveals this fundamental unity then. The mechanism driving the pressure is the thermal entropic motion of the individual particles, and it doesn't matter if they are trapped in the liquid or free in a vacuum.
The core drive is the same. The formula holds up beautifully for dilute solutions because then the solute molecules rarely interact with each other, which mimics the core assumption of an ideal gas.
And this osmotic pressure is not just some laboratory curiosity. It's an immense force that dictates the mechanics of life itself.
It is absolutely critical in all biological systems. The source highlights the most spectacular example, how trees transport water.
Right, because simple suction negative pressure can only lift a column of water about 10 meters before it breaks.
It cavitates. A redwood tree, which can be 100 meters tall, needs a much, much stronger force.
And that force is osmosis, driven by concentration gradients in the root tissues and the leaves.
The roots maintain a higher concentration of solutes than the surrounding soil water. This osmotic pressure difference, combined with capillary forces, creates an immense pulling power, constantly drawing water upward molecule by molecule against gravity. Without this astonishing thermodynamic mechanism, the large structures of life as we know them would be physically impossible.
What an incredible journey into the world outside of perfect balance. We started with the simple, relentless push for higher entropy, the universal mandate for disorder.
And that drive led us directly to these quantitative laws of transport Fourier, Fick, and the Stokes-Einstein relationship.
We've seen that these laws are, at their core, all variations on a single unifying principle. The universe is a smoothing machine.
Whether it's conduction flattening temperature peaks, or diffusion smoothing concentration differences, or even convection organizing itself into those beautiful hexagonal cells, the goal is always uniformity.
And we witness the incredible power of these mathematical frameworks to solve fundamental mysteries, yielding the incontrovertible proof of the atom just from analyzing Brownian motion.
And finally, we saw the ghost of the ideal gas law drives the immense biological engine of osmosis.
The takeaway here really is to try and see the world with thermodynamic eyes.
I think that's right. Every single process you witness, every cup of tea cooling, every scent wafting across a room, every plant drawing moisture, it's a real-time manifestation of these universal transport laws. We are constantly witnessing the slow, relentless pursuit of maximal disorder, and these beautiful equations just dictate the rate at which the universe settles down.
It's a reminder that change isn't chaos. It's highly ordered movement towards a mathematically defined destination. Thank you for diving deep with us today. Until next time.